Today's topic is haloalkanes and haloarenes. Replacement of hydrogen atom in the hydrocarbon, whether it is aliphatic or aromatic, by the halogen atoms will give you what is known as the haloalkanes or haloarenes. Now let us come to the classification. On the basis of number of halogen atoms, they can be classified as monohalogen, dihalogen or trihalogen. If single halogen is present, it will be monohalogen, which is known as the monohaloalkane. If it is 2, it is known as dihaloalkane, and if it is 3, it is known as trihaloalkane. So on the basis of number of hydrogen atom, it can be mono, di or tri. Now let us come on the basis of the nature of the carbon to which the halogen is attached. It can be primary, secondary, tertiary, allylic, benzylic, vinylic or arylic. So if it is attached to a primary carbon, it can be primary. It can be secondary if it is attached to secondary carbon. It can be tertiary if it is attached to tertiary carbon. It can be allylic if it is attached to the allylic carbon. Allylic means C double bond C, you have to see the next carbon to which the halogen is attached. Or it can be vinylic if it is attached to the carbon which is having C double bond C. So depending on the nature of carbon, it is of these types. Now let us come to the nomenclature. For nomenclature, you have to follow certain rules. First is the longest chain rule, that is longest chain of carbon atom bearing the halogen atom will be selected. Secondly, the numbering has to be done in such a way that the halogen gets the least number. So you can see here 2 examples I have taken. So in this chlorine is given number 2, in this chlorine is given number 3, so this one will be the correct one. Now for naming it, you will be using halo as a prefix. That is, if chlorine is there, so you will be using 2-chlorobutane. Besides that, you have to see that if unsaturated alkyl halides are present, then unsaturated bonds, they are given priority than the halogen substituents. And in case of substituents, you have to see if more than one chlorine is present, then numbering can be done on the basis of alphabets. So let us come to the example. You can see here unsaturation is there, halogen is also there, so preference will be given to the unsaturation. So numbering will be such that this get the first number. So this will be 5-chloro 2-methyl pent 2-ene. Now if 2 halogens are present, then the numbering will be on the basis of alphabets. That is, B come first. So first you have to write this and then chlorine. So this will be 4-bromo 5-chloro pent 2-ene. Sorry, 1-ene. Now let us come to the haloarenes. The prefix chloro, bromo, iodo, they are added to the name of the arene. So this will be chlorobenzene, this will be 4-bromo chlorobenzene, this will be 2-chlorotoluene. Now let us talk about the physical properties of aryl halides. When we talk about the physical properties of aryl halides, the lower alkyl halides are gaseous in nature. Up to carbon 18 they will be colorless liquid, and beyond carbon 18 they will be colorless solid. They are soluble in organic solvent, but they are not soluble in water, because in water they cannot form a proper hydrogen bonding. When we talk about the melting and boiling point, the melting and boiling point increases with increase in the size of the alkyl group or increase in the size of the halogen. So this will be the order, that is Ri will be having higher boiling point. It also depends on, as I told you, increase in the size of the alkyl group. Now the melting and boiling point of haloalkanes and haloarenes, they are higher than their parent hydrocarbons, because greater molecular mass is there, so greater van der Waals forces of attraction will be there. Density order will be, this will be the trend for the density order, and in case of bond strength it decreases when you increase the size of the halogen. So in case of bond size, the trend will be CH3F first, then Cr3Cl, then Br, and then I. Now let us talk about the preparations of alkyl halides. First preparation, you can do direct halogenation also. Here first preparation is shown from alcohols. So from alcohol, if you treat it with Lucas reagent, that is HCl and anhydrous ZnCl2, this will be replaced by Cl, and you will be getting alkyl halide and water. Now in this case, the ZnCl2 which you are using, it is used to weaken the carbon OH bond, and secondly, it absorbs the water from the reaction mixture, thus preventing the reverse reaction. It can also be prepared by alcohol when you reflux it with NaBr in presence of sulfuric acid. It can be prepared from phosphorus trihalite. In this case, as you know, phosphoric acid is formed as a byproduct. So you will be using 3 ROH reacting with PX3. So 3R, they will be replacing this OH, and what is left is phosphoric acid. With PCl5, it will be giving you POCl3 and HCl as a byproduct. It can also be prepared from SOCl2 in presence of pyridine. In that case, it will be giving alkyl halide, SO2 and HCl as a byproduct. Now it is known as Darson process, and it is very economical since these two, they are in gaseous form, so it will escape and you will get a pure alkyl halide. Alkyl halides can also be prepared from alkenes either by Markovnikov rule or anti-Markovnikov rule. Now according to Markovnikov rule, if you see, this is the addendum. So negative part of the addendum, negative part means bromine of the addendum, will get attached to the carbon which is having least number of hydrogen. So Br will be attaching here. So there should be a positive side. So migration of these electrons will occur. As a result, this will become positive. So bromine can attach here. Now this being negative, hydrogen will attach here. So you will get a compound like this. That is 2-bromopropane. In anti-Markovnikov rule, peroxide effect, free radical mechanism is applied. So negative part will attach to the carbon which is having more hydrogen. So you will be getting this as a product. Here you are getting 2-bromopropane as a major product. Here we are getting 1-bromopropane as a major product. Now let us talk about the chemical properties or reactions. First reaction is hydrolysis. Alkyl halides, they go hydrolysis on heating in presence of NaOH or KOH. So when you heat it, this will be replaced. This takes place in presence of water, aqueous NaOH or KOH you will be taking. So this will be replaced, you will be getting ROH and NaX. Similarly with KOH, the reaction will occur. Now second reaction is nitrite and nitro formation. Now alkyl halides, if you react it with sodium nitrite or potassium nitrite in ethanolic medium, it will give you nitro and nitrite compounds. Now in case of KNO2, it is ionic in nature. So if it is ionic, you can write it as K plus and ONO minus. Now in this case, this will be plus and this will be minus. So the point of attachment will be through O. So you will be getting here nitrite, ONO. Whereas in AgNO2, it is a covalent compound. So point of attachment will be through nitro. So it will be C2H5NO2. This will be the nitro compound. Now let us come to the nitrile and isonitrile. KCN, in KCN if you see, CN is acting as a nucleophile. So this will be attached to the positive end. While in AgCN as a whole, it acts as a nucleophile. So with AgCN, if you see, you will be getting isonitrile. That will be CH3, CH2, CH2, NC. Next is the Williamson's synthesis. In Williamson's ether synthesis, there will be formation of ether from alcohol on reacting with alkyl halide in presence of NaOH. So first will be the abstraction of proton resulting in the formation of alkoxide, that is RO minus. This bond will break and this will be shifted here, so you will be getting an alkoxide. Second will be alkyl halide will attack this alkoxide, and then you can see here RONA reacting with alkyl halide. Now this is negative, so this being positive, it will be attaching here, so you will be getting the required ether. Now let us talk about the substitution reactions. Substitution reaction is the reaction which involves the replacement of one atom or group by another atom or group. So substitution can be nucleophilic if nucleophile is attacking, it can be electrophilic if electrophile is attacking, or it can be free radical. So now let us talk about the nucleophilic substitution, in which alkyl halide will be reacting with a nucleophile. So this being electronegative, it will attract electron towards itself or will become positive, so nucleophile can attack here. Now it is of two types, that is SN1 and SN2. First is the SN1 reaction. In SN1 reaction, this is the first order reaction, so rate of reaction will be depending on only the concentration of substrate. As you can see here, rate of reaction is directly proportional to the concentration of the substrate. Now example, I have taken tertiary carbon reacting with OH. So this being electronegative will pull electron, it will become positive, so nucleophilic attack will occur. Now this mechanism, it occurs in two steps. So in first step there will be formation of carbocation, and in second step will be the nucleophilic attack. So here this being electronegative will pull electron towards itself, it will become carbocation, and then the nucleophilic attack will occur. Now this nucleophilic attack, it can take place from the front side or it can take place from the back side, resulting in the retention or inversion of configuration. So when we talk about the stereochemistry of SN1, there will be racemization with 50% retention, 50% inversion. So it will be a racemic mixture. When we talk about the reactivity, tertiary will be more reactive as compared to the secondary, and that will be more reactive as compared to the primary, because more the stability, more rapidly is the carbocation formed. So tertiary carbocation is more stable, so faster will be the reaction. When we talk about the energy profile diagram, this will be the energy profile diagram. Since intermediate is formed, it is a two-step reaction, so it will be showing the difference in the energy. Now let us talk about the SN2 reaction. This is a second order reaction, so rate of reaction will be depending on the concentration of the substrate as well as the nucleophile. It is one step reaction, that is the leaving group and the incoming group. They will be acting simultaneously. So that will result in the formation of pentavalent transition state, which is highly unstable. This dotted line shows that either the bonds they are breaking or new bonds are forming. So this is bond is breaking and this is forming. Now since the leaving group is going and nucleophile is attacking from the back side, so it will lead to the inversion in the configuration. So when we talk about the stereochemistry, we will say there will be inversion in the configuration. Reactivity, primary will be more reactive than secondary and then tertiary, because if tertiary group is present, all the bulky groups, they will be very close to each other, so it will be difficult for the nucleophile to attack. This will be the potential energy diagram. Now let us talk about SNI reaction, that is nucleophilic substitution first order reaction. Such reaction takes place in two steps, and in this case there will be retention of the configuration. It is different from SN1 because in this ion pair is not completely dissociated, so no real carbocation will be formed, and which otherwise would lead to racemization. So if you see here in this, what is happening is first the HCl it is going, so this O will get attached to this, you are getting this product, and then in between rearrangement will occur, this bond will break, this electron it will shift here, this will become positive, again this will take the electrons, this will become negative, so this can attack here. as you can see here. So you are getting HCl and SO2 as a byproduct. Now let us talk about the elimination reaction, in which the removal of simple groups will take place, resulting in the formation of multiple bonds. So elimination can be of two types, that is E2 elimination and E1 elimination. E2 elimination, again 2 means it is a second order reaction, so rate of reaction will be depending on the substrate and the base, but it is one step reaction, that is the removal of the base and removal of the leaving group and abstraction of hydrogen by the base. It will occur at the same time, resulting in the formation of intermediate transition state, which is highly unreactive, and that will finally give you the product. Now if you see here, bromine being electronegative will pull electron towards itself. This will become unstable, so at the same time hydrogen is abstracted by the base, so it will leave its electron here, so double bond will be formed here. So dotted line, it tells you either the bonds they are breaking or new bonds are forming. So finally this will be living as water, and you are left with the alkene. Second is E1 elimination, which is a two-step reaction, but it is a first order reaction, so rate of reaction will depend on the concentration of only the substrate. So in first step, carbocation will be formed. Since bromine being electronegative, it will pull electron, and this carbon will be forming the carbocation. Now in second step, there will be abstraction of hydrogen by the base. So this abstraction can take place as per the ZZEF rule, in which hydrogen will be eliminated from that beta carbon which is having least number of hydrogen, resulting in the formation of alkene. So this is the ZZEF rule. In this case, if you see this example, there are 3 beta carbons. So hydrogen will be eliminated from that beta carbon which is having least number of hydrogen. This is having 3, this is having only 1, 2. So hydrogen will be eliminated from here. So this will be the major product, and the other one will be the minor product. In case of Aryl Halides, they can be prepared by direct halogenation, as you can see here, in which you are taking benzene, reacting it with halogen in presence of sunlight. This is giving you Aryl halide. For iodine, it is little bit difficult, because it is not a useful reaction, as Hi which is formed, it will react back to form the aromatic hydrocarbon. So in presence of oxidizing agent like nitric acid or hydroiodic acid or HGO, the Hi produced, it will be either oxidized to iodine or it is eliminated as mercuric iodide, as you can see here. Fluorobenzene cannot be prepared by direct fluorination of aromatic hydrocarbons, as it is a very violent reaction and it cannot be controlled. Now from diazonium salt also you can prepare. So for that, first you have to do diazotization, in which aniline, primary amine you will take like aniline, and you are reacting it with NaNO2 in presence of dilute HCl at low temperature. So it will give you a diazonium salt. This diazonium salt on treatment with CuCl or CuBr in presence of halogen acid will give you the corresponding aryl halide. As you can see here, chlorobenzene, you are getting bromobenzene here. In presence of Ki, it will give you iodo, and HBF4 it is giving you fluoro. So this reaction was carried out by Sandmeyer, so it is known as the Sandmeyer's reaction. Second is the Gattermann reaction, in which the haloarenes can also be prepared by reacting the benzene diazonium salt directly with the copper powder and in presence of halogen acid, so that will give you the corresponding haloarenes. From phenols also you can make it, that is phenol reacting with PCl5 giving you the corresponding haloarene. But with PCl5 you are getting POCl3 and HCl as a byproduct. Now let us talk about the reactions. They react with NaOH, so they will give you the corresponding phenol. Now aromatic nucleophilic substitution is somewhat difficult because it may be due to resonance, that is CX bond, it is having a partial double bond character, or it can be due to stabilization of molecule by delocalization, or instability of phenyl carbocation. However, aryl halides which are having electron withdrawing group like NO2 sulfonic group, they show substitution at ortho and para position. So presence of electron withdrawing group increases the reactivity. You can see here. So presence of electron withdrawing group increases the reactivity. So substitution is occurring easily. When we talk about electrophilic substitution reaction, whether it is chlorination, nitration, sulfonation, Friedel-Crafts reaction, you will be getting ortho and para substituents. So chlorination, you are getting ortho and para. In one will be the major product, other will be the minor product. Similarly, nitration in presence of nitric acid, nitro group at ortho and para position. When we talk about Friedel-Crafts alkylation, so alkyl group, it will be attached again at ortho and para position. When we talk about acylation, acyl group will be attached again at ortho and para position. Now let us talk about the reaction of aryl halides with metal. With metal, it gives you different reactions like Wurtz-Fittig reaction, Fittig reaction, Ullmann reaction. So in this again, in presence of sodium, this occurs in ether medium. So alkyl group will be replaced here, and NaX, 1X from here, that is giving you this product. Similarly, if you see here, if you are taking twice of this, you will be getting a diphenyl here. And in Ullmann reaction, you are treating it with iodobenzene and copper powder, you will get biphenyls. Finally, let us compare the reactivities of aryl halide, vinyl halide and alkyl halide first. Aryl chloride is more reactive in comparison to alkyl halide, since it gives more stable intermediate carbocation due to the resonance. It will be stabilized and they can further furnish more stable carbocation. So they are more reactive. Even in SN2 reaction, aryl halides, they will show greater reactivity due to its linear shape. And vinyl chloride, it is less reactive because due to resonance, in this case, double bond is formed between C and Cl, so it will be very difficult to break this bond. So when we compare the reactivity order will be aryl halides, they are more reactive than alkyl halide, and they are more reactive than vinyl. So in vinyl, due to double bond formation, they show least reactivity. So when we talk about aryl halides, they undergo nucleophilic substitution under drastic conditions. For example, you can see chlorobenzene, they show low reactivity towards alkyl halides. Then alkyl halides towards nucleophilic substitution, since they are resonance stabilized. But if powerful electron withdrawing group, as I told you earlier, they are present, so then a nucleophilic substitution can easily take place in ortho and para position. So you can say here electron withdrawing group is present, so nucleophilic substitution is occurring. On the other hand, if electron releasing group is present like NH2, OH, OR, they will deactivate the aryl halide towards the nucleophilic substitution. So here I have taken 3 examples. One is parachlorobenzene, other is chlorobenzene, third one is parachloroanisole. Now this is electron withdrawing, this is electron donating, releasing. So if you compare the reactivity, since it is electron withdrawing, it will be showing maximum reactivity, and this will show least reactivity due to electron donating nature.